Hello there. I'm so glad you found your way here tonight. Somewhere far beneath the surface of our world lies a realm of absolute stillness. A place where sunlight fades into endless blue, where mountains rise taller than any on land, and where creatures glow with their own soft light in the eternal darkness. The ocean covers more than 70% of our planet. Yet most of it remains unseen, unmapped, and unexplored. Tonight, we embark on a tranquil journey beneath the waves. We will drift through over 100 soothing facts about the ocean, from ancient shipwrecks resting on the seafloor to creatures that defy the boundaries of life and death, from underwater volcanoes to forests of kelp that sway in silent currents. There is no test at the end, no rush, no urgency, just the gentle unfolding of the ocean's most extraordinary secrets to carry you softly towards sleep. So let your breathing slow. Let your thoughts drift like the gentle tides. And allow yourself to sink peacefully into the quiet wonder of Earth's largest habitat. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the vast and mysterious world beneath the waves. Either way, this space is for you. There is something deeply calming about contemplating the ocean. Every wave, every current, every hidden depth carries within it a story, billions of years in the making. You are connected to this story. The water in your body has cycled through the ocean countless times. The oxygen in your lungs may have been released by a tiny plankton drifting somewhere in the Pacific just weeks ago. The salt in your tears and blood mirrors the chemistry of the ancient seas where life first began. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let the weight of the day drift away like foam, dissolving on a quiet shore. And let us begin with the first of many peaceful truths about the ocean. The ocean is patient beyond measure. Currents move in cycles that span centuries. Mountains form grain by grain over millions of years. Creatures live in rhythms set by the moon and the tides, unchanged since before the dinosaurs walked the earth. Tonight, we will wander through this magnificent world. We will meet creatures larger than any dinosaur. We will discover places deeper than any mountain is tall. And we will uncover truths about the ocean that may surprise even the most curious minds. But there is no hurry. The ocean has been here for 4 billion years. It can wait a little longer while you rest. Let us begin with the hidden depths. The deepest part of the ocean is deeper than Mount Everest is tall. At the bottom of the Mariana Trench lies Challenger Deep, a place so far beneath the waves that if you placed Mount Everest into it, the summit would still be submerged by more than a mile of water. The pressure at this depth is over 1,000 times greater than at the surface, enough to crush most human-made equipment. Only a handful of people have ever descended to this realm, fewer than have walked on the moon. The journey down takes hours, passing through zones of perpetual darkness where no sunlight has penetrated for billions of years. Yet even here, in conditions that seem utterly hostile to existence, life persists. Strange creatures adapted to immense pressure and eternal cold drift through waters that humans can barely imagine. Challenger Deep reminds us that the deepest parts of our planet remain more mysterious than the surface of distant worlds. more than 80% of the ocean remains unexplored. Despite centuries of maritime adventure and decades of advanced technology, the vast majority of the ocean floor has never been mapped, photographed, or visited by human eyes. We have better maps of Mars and the Moon than we do of our own sea floor. The challenges are immense, as the ocean is vast, deep, and hostile to human exploration. Submersibles capable of reaching the deepest trenches are rare and expensive to operate. Satellite imaging cannot penetrate the darkness below the surface. Every expedition to the deep reveals new species, new geological formations, and new mysteries. Scientists estimate that millions of marine species remain undiscovered, waiting in the darkness for their first encounter with humanity. The ocean is Earth's last great frontier, and most of its secrets are still locked in the unexplored depths. The ocean's abyssal plains are among the flattest places on Earth. Far beneath the waves covering vast areas of the ocean floor lie the abyssal plains. These immense expanses of sediment-covered seafloor are so flat that variations of just a few meters can stretch across hundreds of kilometers. They are formed by the slow accumulation of fine particles drifting down from the surface over millions of years, blanketing the original seafloor topography like snow covering a landscape. The sediments contain the remains of countless microscopic organisms, each layer a record of the ocean's history stretching back tens of millions of years. Despite their apparent barrenness, the abyssal plains support unique communities of creatures adapted to the extreme cold, darkness, and pressure. Sea cucumbers, brittle stars, and bizarre fish patrol these silent expanses. The abyssal plains remind us that even the most featureless places can harbor hidden wonders. The deep sea is the largest habitat on Earth by volume. When we think of habitats, we often picture forests, deserts, or grasslands, but the largest living space on our planet lies beneath the ocean surface. The deep sea, defined as waters below 200 meters where sunlight cannot penetrate, makes up over 90% of the ocean's total volume. This vast realm stretches from the twilight zone, where the last glimmers of light fade, to the abyssal depths, where darkness is absolute and eternal. The deep sea is home to more species than all other habitats combined, though most remain undiscovered. Creatures here have evolved extraordinary adaptations to survive the crushing pressure, near freezing temperatures, and complete absence of light. The deep sea is not a barren wasteland, but a thriving wilderness, larger and more diverse than all the land habitats on Earth combined. The ocean's deep trenches are some of the least explored places on our planet. Ocean trenches form where tectonic plates collide and one slides beneath another, creating narrow chasms that plunge to depths of 10 kilometers or more. These trenches are among the most extreme environments on Earth, with pressures that would crush submarines and temperatures hovering just above freezing. Only a handful of expeditions have ever reached the bottom of the deepest trenches, and each descent has revealed creatures never seen before. Giant amoebas, ghostly fish, and shrimp-like amphipods thrive in conditions that would kill most life instantly. The trenches also play important roles in Earth's geology, recycling oceanic crust back into the mantle over millions of years. Exploring these extreme environments requires technology at the very edge of human capability. The trenches remain some of the last truly unexplored territories on our planet. Underwater canyons can be deeper than the Grand Canyon. Carved into continental shelves and slopes around the world are underwater canyons that rival and often exceed the dimensions of their famous terrestrial counterparts. Monterey Canyon off the California coast plunges deeper than the Grand Canyon and stretches for nearly 100 kilometers. These submarine canyons were carved by underwater currents, carrying sediment-laden water from rivers and continental shelves down into the deep ocean. They serve as highways for marine life, channeling nutrients from shallow waters to the deep sea and providing habitat for countless species. Whales, sharks, and deep-sea fish patrol their depths, while their walls harbor diverse communities of invertebrates. The canyons are dynamic environments, shaped by underwater landslides and turbidity currents that can travel at speeds exceeding motorway traffic. Beneath the seemingly calm surface of the sea, landscapes as dramatic as any on land await discovery. The longest mountain range on Earth lies beneath the ocean. The mid-ocean ridge system stretches for over 65,000 kilometers around the globe, winding through every ocean like the seam on a baseball. This underwater mountain chain dwarfs any range found on land, making the Himalayas and the Andes seem modest by comparison. The ridge marks the boundaries where tectonic plates are slowly pulling apart, allowing molten rock to rise from the mantle and create new oceanic crust. The process is continuous and has been occurring for billions of years, reshaping the face of the Earth with each passing millennium. The mountains of the mid-ocean ridge rise several kilometers from the seafloor, yet most remain hidden from view beneath miles of dark water. In some places, like Iceland, the ridge breaks the surface, offering a rare glimpse of this underwater realm. The mid-ocean ridge is a reminder that the most dramatic geological features on our planet are not found on land, but hidden beneath the waves. Underwater volcanoes create new land and influence ocean chemistry. Beneath the surface of every ocean, thousands of underwater volcanoes rise from the seafloor, some reaching heights that rival the tallest mountains on land. These submarine volcanoes erupt constantly, pouring molten rock into the cold waters and creating new seafloor at rates that shape the planet over geological time. Some underwater volcanoes grow tall enough to break the surface, forming new islands like Hawaii and Iceland. The eruptions release gases and minerals into the ocean, influencing the chemistry of seawater on a global scale. Iron, manganese, and other elements essential for life are distributed by volcanic activity, supporting ecosystems far from the eruption sites. The heat from these volcanoes creates thermal plumes that can be detected thousands of kilometers away. Underwater volcanoes are not just geological curiosities, but active forces that continuously reshape our ocean and influence the chemistry of the entire marine environment. Hydrothermal vents support unique ecosystems powered by chemicals instead of sunlight. In the darkness of the deep ocean, far from any sunlight, hydrothermal vents create oases of life that defied scientific expectations when they were first discovered. These vents form where seawater seeps into cracks in the seafloor, becomes superheated by magma below, and erupts back into the ocean laden with dissolved minerals. The water emerging from black smokers can reach temperatures exceeding 400 degrees Celsius, yet the extreme pressure at depth prevents it from boiling. Around these vents, bacteria use chemical energy from hydrogen sulfide and other compounds to produce food through chemosynthesis, supporting entire ecosystems without any input from the sun. Giant tube worms, ghostly crabs, and strange fish thrive in these environments, forming communities as diverse as any coral reef. The discovery of hydrothermal vent ecosystems revolutionized our understanding of where life can exist. These otherworldly communities suggest that life might survive in similar environments on distant moons and planets. The ocean contains underwater lakes and rivers with different chemistry. Beneath the Gulf of Mexico and in other regions around the world, divers and submersibles have discovered something remarkable: lakes and rivers flowing along the ocean floor. These underwater bodies of water form when dense brine, far saltier than the surrounding seawater, pools in depressions on the seafloor. The difference in salinity creates a distinct boundary between the brine and the overlying water, visible as a shimmering surface that resembles the interface between air and water. Fish and other creatures can be seen swimming along the edges of these brine pools, unable or unwilling to enter the toxic waters below. The chemistry of these underwater lakes is often hostile to most life, with extremely high concentrations of salt and methane. Yet specialized bacteria thrive in these extreme conditions, processing chemicals in ways that support unique food chains. These underwater lakes are among the strangest features of the ocean floor, defying our intuition about what lies beneath the waves. Natural oil seeps on the seafloor support unique communities. Long before humans drilled for oil, natural seeps have been releasing petroleum into the ocean from fractures in the seafloor. These seeps occur where oil and gas deposits are not fully sealed by overlying rock, allowing hydrocarbons to escape slowly into the water column. Rather than creating lifeless zones, these seeps support thriving communities of specialized organisms. Bacteria have evolved to metabolize the oil, forming the base of food chains that include mussels, clams, and tube worms. The communities around cold seeps share similarities with those at hydrothermal vents, relying on chemical energy rather than sunlight. Some of these seep communities have persisted for thousands of years, growing slowly in the cold, dark waters of the deep ocean. The tar and oil that emerge from these natural seeps eventually rise to the surface, where they have been washing ashore for millions of years. Natural oil seeps remind us that the ocean has been recycling hydrocarbons long before the age of petroleum. The ocean's thermohaline circulation acts like a global conveyor belt. Deep beneath the surface, the ocean moves in a vast slow-motion current that connects every ocean basin on Earth. This thermohaline circulation, driven by differences in temperature and salinity, takes water on a journey that can last over 1,000 years. Cold, dense water sinks near the poles, travels along the sea floor toward the equator, rises in warmer regions, and eventually returns to the polar seas to begin the cycle anew. This great oceanic conveyor belt redistributes heat from the tropics toward higher latitudes, moderating the climates of entire continents. The circulation also carries dissolved gases, nutrients, and carbon dioxide to the deep ocean, where they remain locked away for centuries. Changes in this circulation have been linked to dramatic climate shifts in Earth's past, including ice ages and sudden warming events. The thermohaline circulation is the slow, steady heartbeat of the global ocean, quietly shaping our world. Ocean currents regulate global climate. The ocean's currents act as a planetary thermostat, moving vast amounts of heat from the tropics toward the poles, and keeping global temperatures far more stable than they would otherwise be. The Gulf Stream alone carries more heat than all the world's power stations combined, warming the coasts of Western Europe and allowing cities like London and Paris to enjoy mild winters. Without these currents, tropical regions would be unbearably hot, while higher latitudes would be locked in permanent ice. Currents also influence weather patterns, determining where rain falls and where deserts form. The interaction between ocean currents and atmospheric circulation creates the monsoons that billions of people depend upon for water and agriculture. Understanding ocean currents has been essential for navigation, fishing, and predicting weather for centuries. These invisible rivers flowing through the sea are among the most powerful forces shaping life on Earth. Ocean waves can travel thousands of miles without losing energy. When a storm rages in the open ocean, the energy it imparts to the water begins a journey that can span entire ocean basins. These swells travel outward from the storm in ever-widening circles, maintaining their form and energy across thousands of kilometers of open water. Unlike wind waves that are chaotic and short-lived, swells are organized and persistent, carrying the memory of distant storms to shores they will never see again. Surfers in Hawaii ride waves generated by storms near Antarctica, while beaches in Europe receive swells born in the hurricanes of the Caribbean. The longer the wave travels, the more it organizes itself, with longer period waves moving faster and arriving first. Waves carry tremendous energy, enough to reshape coastlines, power cities, and remind coastal communities of storms that occurred days ago and thousands of miles away. The ocean's ability to transmit energy across such vast distances is one of its most remarkable and humbling properties. The ocean has its own weather systems, like underwater vortices. Just as the atmosphere has storms and jet streams, the ocean has its own dynamic weather systems that swirl through the depths. Underwater vortices, or mesoscale eddies, spin through the ocean like slow-motion hurricanes, ranging from a few kilometers to hundreds of kilometers in diameter. These eddies form when currents become unstable, breaking off into spinning parcels of water that can persist for months or even years. They trap water with distinct temperature and salinity signatures, carrying it across ocean basins like floating reservoirs. Eddies influence everything from the distribution of marine life to the pathways of debris and pollutants. Some spin clockwise, some anti-clockwise, and their rotation determines whether they draw water up from the depths or push it down. Oceanographers study these underwater weather systems using satellites, drifting buoys, and autonomous vehicles. The ocean's internal weather is just as complex and dynamic as the weather we experience on land. Ocean eddies can trap nutrients and support localized marine productivity. Spinning eddies in the ocean are not merely physical phenomena, but biological engines that can concentrate life in unexpected places. When an eddy spins in a way that draws water upward from the depths, it brings nutrients that have sunk below the sunlit zone back into the light. These nutrients fuel blooms of phytoplankton, which in turn attract zooplankton, fish, seabirds, and marine mammals. Some eddies become oases of productivity in otherwise nutrient-poor waters, visible from space as bright green patches against the dark blue sea. The spinning motion of the eddy can trap organisms within its core, creating temporary ecosystems that drift across the ocean. Fishermen have long known to seek out these areas, following cues that science is only now beginning to understand. Eddies can also transport larvae and juvenile fish across ocean basins, connecting distant populations and maintaining genetic diversity. These swirling currents are essential components of the ocean's complex web of life. Upwelling brings nutrient-rich deep waters to the surface. Along certain coastlines and in the open ocean, deep waters rise toward the surface in a process called upwelling, carrying nutrients that have accumulated in the darkness below. These nutrients, including nitrogen, phosphorus, and iron, fuel explosive growth of phytoplankton at the surface, forming the base of some of the most productive food chains on Earth. Upwelling zones support vast populations of fish, which in turn attract seabirds, marine mammals, and commercial fishing fleets. The coastal upwelling zones off Peru, California, and West Africa are among the most productive fisheries in the world, supporting industries worth billions of dollars. Upwelling is driven by winds that push surface waters away from the coast, allowing deeper waters to rise and replace them. Seasonal changes in wind patterns create predictable cycles of productivity that have shaped human cultures and economies for millennia. Upwelling is the ocean's way of recycling nutrients and sustaining life on a scale that is almost impossible to comprehend. The ocean's salinity varies across different regions. Although we speak of the ocean as salty, the degree of that saltiness changes dramatically from place to place. Near the mouths of great rivers like the Amazon and the Congo, fresh water pours into the sea, diluting the salt and creating vast plumes of brackish water that extend hundreds of kilometers offshore. In the subtropics, where evaporation exceeds rainfall, the ocean becomes saltier than average, concentrating minerals as water vapor rises into the atmosphere. The Mediterranean Sea, nearly enclosed by land and subject to intense evaporation, is notably saltier than the Atlantic Ocean that feeds it. The Baltic Sea, receiving abundant fresh water from rivers and rainfall, is among the least salty seas on Earth. These variations in salinity create invisible boundaries in the ocean, separating water masses with different properties and influencing where marine life can thrive. The salt in the sea is not uniform but varies in concentration, creating a complex mosaic of conditions beneath the surface. The ocean's salt is primarily derived from volcanic activity and rock weathering. The salt that fills the ocean has accumulated over billions of years, arriving through processes that continue to this day. When rain falls on land, it slowly dissolves minerals from rocks and carries them in rivers to the sea. Volcanic eruptions, both on land and beneath the ocean, release gases and minerals that react with seawater to form salts. Hydrothermal vents pump dissolved chemicals directly into the deep ocean, adding to the oceanic reservoir of minerals. Once dissolved in the ocean, these salts have no easy escape. Water evaporates from the surface, rises into the atmosphere, and falls as fresh rain, but the salts remain behind, concentrating over geological time. The composition of sea salt is remarkably consistent around the world, containing sodium, chloride, magnesium, sulfur, calcium, and potassium in predictable proportions. The ocean is a vast chemical archive, recording billions of years of geological and volcanic activity in its salty waters. The ocean's salt content has remained stable for millions of years. Despite the continuous input of minerals from rivers, volcanoes, and hydrothermal vents, the overall salinity of the ocean has remained remarkably stable for hundreds of millions of years. This stability reflects a balance between inputs and outputs that operate over geological timescales. Salt is removed from the ocean when seawater becomes trapped in sediments, when minerals precipitate on the seafloor, and when sea spray deposits salt on land. The formation of massive salt deposits, visible today in places like the Dead Sea and ancient salt mines, represents episodes when sections of ocean became isolated and evaporated. The steady-state salinity of the modern ocean is not an accident, but the result of complex feedback mechanisms that regulate Earth's chemistry. Life has evolved to depend on this stability, with marine organisms finely tuned to the precise salt concentration of their environment. The constancy of ocean salinity is one of the quiet miracles that makes life in the sea possible. Salt water is heavier than fresh water, causing natural layering. The density difference between salt water and fresh water creates invisible architecture within the ocean, separating layers of water that barely mix despite being in contact for centuries. Where rivers meet the sea, fresh water floats on top of the denser salt water below, creating estuaries with distinct upper and lower layers, inhabited by different communities of life. In the open ocean, differences in salinity and temperature create stratification that influences everything from nutrient distribution to climate. The halocline, a sharp boundary where salinity changes rapidly with depth, can be so distinct that divers describe the sensation of passing through it as pushing through jelly. This layering traps nutrients in certain zones, influences where organisms can live, and affects how the ocean mixes and circulates. Submarines have long used these density differences to hide, sitting motionless in layers that reflect sonar signals. The invisible architecture of salinity gives the ocean a three-dimensional structure, far more complex than its seemingly uniform surface suggests. The ocean contains more gold than all the gold mines on land. Dissolved in the vast volume of the world's oceans is an astonishing quantity of gold, estimated at over 20 million tons. This treasure trove exceeds all the gold ever mined in human history by a factor of hundreds. Yet extracting this gold remains economically impractical, as it is dispersed in concentrations of only a few parts per trillion, mixed with the trillions of tons of water that fill the ocean basins. Early attempts to harvest oceanic gold, including efforts by desperate governments after the First World War, proved utterly futile. The gold arrived in the ocean dissolved in river water and released from underwater volcanic activity, accumulating grain by invisible grain over billions of years. Besides gold, the ocean contains significant quantities of silver, uranium, and nearly every other element on the periodic table. The ocean is a vast chemical storehouse, holding riches beyond imagination, in concentrations too diffuse to extract. Perhaps this is for the best, leaving the ocean's wealth safely dissolved in its salty embrace. The ocean absorbs around 30% of human-produced carbon dioxide. Every year, the ocean quietly absorbs billions of tons of carbon dioxide from the atmosphere, acting as a massive buffer against the worst effects of climate change. This absorption occurs through two main processes: the physical dissolution of carbon dioxide into cold surface waters, and the biological uptake by phytoplankton during photosynthesis. Without this oceanic sponge, atmospheric carbon dioxide levels would be far higher than they are today, and global temperatures would have risen even more dramatically. The carbon absorbed at the surface is gradually transported to the deep ocean by sinking currents and falling organic matter, where it can remain locked away for centuries. However, this service comes at a cost to the ocean itself, as the absorbed carbon dioxide reacts with seawater to form carbonic acid. The ocean's capacity to continue absorbing carbon at current rates is uncertain, with some scientists warning that warming waters may become less efficient at this vital task. The ocean has been quietly protecting us, but this protection may have limits we are only beginning to understand. The ocean holds nearly 20 times more carbon than the atmosphere. The vast volume of the ocean contains an enormous reservoir of carbon, far exceeding the amount stored in the atmosphere, forests, and soils combined. Most of this carbon exists as dissolved inorganic compounds, including bicarbonate and carbonate ions, the same chemicals that give seawater its slight alkalinity. Organic carbon is also present in the form of dissolved compounds, living organisms, and the constant rain of dead material sinking toward the seafloor. The deep ocean acts as a long-term carbon storage facility, holding carbon dioxide that entered the water centuries or even millennia ago. This carbon moves slowly through the ocean, carried by currents and biological processes that operate on timescales far longer than human lifetimes. The exchange of carbon between the ocean and atmosphere helps regulate Earth's climate, but changes in this balance can have profound consequences. Understanding the ocean's role in the carbon cycle is essential for predicting how our planet will respond to continued emissions of greenhouse gases. Ocean acidification threatens shell-building creatures. As the ocean absorbs more carbon dioxide from the atmosphere, its chemistry is changing in ways that threaten some of its most important inhabitants. The dissolved carbon dioxide reacts with seawater to form carbonic acid, lowering the ocean's pH in a process known as ocean acidification. Since the Industrial Revolution, the ocean has become approximately 30% more acidic, a rate of change unprecedented in millions of years. This acidification makes it harder for shell-building organisms like corals, oysters, and certain plankton to construct their calcium carbonate structures. Laboratory experiments show that some species struggle to grow shells in more acidic conditions, while others dissolve entirely. These organisms form the foundation of marine food webs and build structures like coral reefs that support thousands of other species. The long-term consequences of ocean acidification are still unfolding, but scientists warn that continued acidification could fundamentally alter marine ecosystems. The ocean's chemistry is changing faster than many organisms can adapt. The ocean's surface temperature has risen significantly over the past century. Over the past 100 years, the average temperature of the ocean's surface has increased by approximately 1 degree Celsius, a change that may seem small but has profound consequences for marine life and global climate. The ocean has absorbed over 90% of the excess heat trapped by greenhouse gases, buffering the atmosphere but warming the waters. This warming is not uniform, with some regions heating faster than others, and polar waters experiencing particularly rapid changes. Warmer waters hold less dissolved oxygen, forcing some species to migrate toward the poles or into deeper, cooler zones. Marine heat waves have become more frequent and intense, causing mass die-offs of corals, fish, and other organisms. The warming ocean also contributes to more powerful hurricanes and altered weather patterns that affect communities far from the coast. The ocean has absorbed much of the heat we have added to the climate system, but the consequences of this warming are only beginning to manifest. The ocean's surface reflects about 6% of incoming solar radiation. The ocean's vast expanse plays a complex role in Earth's energy balance, absorbing most of the sunlight that reaches its surface, while reflecting a small but significant portion back into space. This reflectivity, or albedo, varies depending on the angle of the sun, the roughness of the sea surface, and the presence of foam or floating particles. Dark, calm waters absorb more heat than choppy seas dotted with whitecaps, and the color of the water itself varies with the concentration of phytoplankton and suspended sediments. The heat absorbed by the ocean drives evaporation, powers hurricanes, and fuels the currents that redistribute warmth around the globe. Changes in ocean color due to declining phytoplankton populations could alter how much heat the ocean absorbs, creating feedback loops that are difficult to predict. The interaction between sunlight and seawater is deceptively complex, involving physics, chemistry, and biology in ways scientists are still working to understand. The ocean's surface is not just a passive receiver of solar energy, but an active participant in the global climate system. The ocean's water cycle plays a major role in global rainfall patterns. Every drop of rain that falls anywhere on Earth has cycled through the ocean countless times over the planet's long history. The ocean is the source of approximately 86% of all evaporation on Earth, sending vast quantities of water vapor into the atmosphere, where it condenses into clouds and falls as precipitation. This water cycle connects the ocean to every continent, delivering the fresh water that fills rivers, lakes, and underground aquifers. The pattern of evaporation from the ocean's surface is not uniform, with tropical waters losing more moisture than polar seas, and some regions evaporating faster than they receive rainfall. These patterns drive the great atmospheric circulation systems that determine where deserts and rainforests form. Changes in ocean temperature and circulation can alter rainfall patterns thousands of kilometers away, affecting agriculture, water supplies, and ecosystems on land. The ocean is the engine of the water cycle, connecting the seas to the skies and the skies to the land in an endless, life-giving circulation. The ocean's ice sheets affect global sea levels and ocean currents. The great ice sheets of Greenland and Antarctica hold enough frozen water to raise global sea levels by over 70 meters if they were to melt completely. These vast reservoirs of ice have been stable for millions of years, but they are now losing mass at accelerating rates as the climate warms. The meltwater flowing into the ocean affects more than just sea levels, as the fresh water is less dense than the surrounding seawater and can disrupt the thermohaline circulation that drives global ocean currents. Changes in these currents could alter weather patterns around the world, affecting rainfall, temperature, and agricultural productivity on every continent. The ice sheets also play a role in reflecting sunlight back into space, and their loss exposes darker ocean and land surfaces that absorb more heat. Scientists monitor the ice sheets using satellites, drilling cores from deep within the ice, and measuring the flow of glaciers toward the sea. The fate of the ice sheets is one of the most consequential uncertainties in predicting our future climate. Sea ice covers around 7% of the ocean's surface, but plays a huge role in climate. Floating sea ice forms a frozen skin over portions of the Arctic and Southern Oceans, covering an area that expands and contracts with the seasons. At its maximum extent, sea ice covers around 7% of the global ocean surface, yet its influence on climate far exceeds its size. The bright white surface of sea ice reflects up to 80% of incoming sunlight, compared to just 6% for dark ocean water. This difference in reflectivity, or albedo, means that as sea ice melts, more heat is absorbed by the ocean, accelerating further warming in a feedback loop that concerns climate scientists. Sea ice also insulates the relatively warm ocean water beneath from the frigid polar atmosphere, affecting heat exchange between sea and sky. The seasonal formation and melting of sea ice drives changes in ocean salinity that influence global circulation patterns. Arctic sea ice has declined dramatically in recent decades, with summer ice extent shrinking to levels not seen in thousands of years. The loss of sea ice represents one of the most visible and consequential changes to our planet. Melting ice changes ocean salinity and circulation patterns. When ice melts, whether from glaciers on land or sea ice floating on the ocean, the fresh water that results is far less salty than the surrounding seawater. This influx of fresh water can create a layer on the ocean surface that resists mixing with the denser, saltier water below. In regions where cold, salty water normally sinks to drive the thermohaline circulation, an excess of fresh meltwater can slow or disrupt this sinking. Changes in the rate of deep water formation have been linked to dramatic climate shifts in Earth's past, including periods of rapid cooling and warming. The Greenland ice sheet is currently releasing hundreds of billions of tons of fresh water into the North Atlantic each year, and scientists are monitoring the region closely for signs of circulation changes. Melting Antarctic ice is similarly affecting the waters around the Southern Ocean, with implications for global climate and marine ecosystems. The relationship between ice, salt, and ocean circulation is complex and full of feedbacks that scientists are still working to understand. The melting of polar ice is not just a local phenomenon but a global event with consequences that ripple through the entire climate system. The ocean's coral reefs are some of the most diverse ecosystems on Earth. Coral reefs occupy less than 1% of the ocean floor, yet support approximately 25% of all known marine species, making them the rainforests of the sea. These vibrant underwater cities teem with fish of every color imaginable, invertebrates hiding in every crevice, and predators patrolling the reef's edge. The structure of the reef itself is built by tiny coral polyps, relatives of jellyfish that secrete calcium carbonate skeletons over generations. Thousands of species have evolved to depend on coral reefs for food, shelter, and breeding grounds, creating complex webs of interaction that scientists are still working to untangle. Reefs also protect coastlines from storms, provide livelihoods for millions of fishermen, and attract tourists from around the world. The biodiversity of coral reefs is not merely beautiful but functional, with each species playing roles that maintain the health of the whole ecosystem. Coral reefs are masterpieces of evolution, built grain by grain over millennia by organisms smaller than your fingernail. Some coral reefs are over 10,000 years old. The oldest living coral reefs began growing at the end of the last ice age, when rising sea levels flooded continental shelves and provided new foundations for reef-building corals. Individual coral colonies can live for thousands of years, growing slowly upward and outward as new polyps build their skeletons atop the remains of their ancestors. Some massive brain corals have been dated to over 2,000 years old, meaning they began growing when the Roman Empire was at its height. The structure of the reef itself represents an even longer legacy, with older skeletons providing the foundation for younger growth. Cores drilled from ancient reefs reveal layers of growth that record changes in ocean temperature, chemistry, and circulation over millennia. These living time capsules allow scientists to reconstruct past climates and understand how reefs have responded to environmental changes throughout history. The reefs we see today are the legacy of countless generations of coral polyps, each adding its tiny contribution to a structure that has outlasted human civilizations. The Great Barrier Reef is the largest living structure on Earth. Stretching for over 2,300 kilometers along the northeastern coast of Australia, the Great Barrier Reef is the largest structure ever built by living organisms. This immense ecosystem comprises nearly 3,000 individual reef systems and hundreds of islands, covering an area roughly the size of Italy. The reef is home to over 1,500 species of fish, over 400 types of coral, and countless invertebrates, mammals, and reptiles. The Great Barrier Reef is so large that it can be seen from space, a bright turquoise jewel against the deep blue of the Coral Sea. Aboriginal Australians have lived alongside the reef for over 60,000 years, developing a deep understanding of its rhythms and resources. Today, the reef faces unprecedented threats from warming waters, ocean acidification, and pollution, but it remains one of the most spectacular natural wonders on our planet. The Great Barrier Reef is a testament to what tiny creatures can build when given millions of years and the right conditions. Coral spawning often happens simultaneously across entire reefs once a year. On certain nights each year, usually triggered by the full moon and rising water temperatures, coral reefs erupt in one of nature's most spectacular events. Billions of coral polyps release their eggs and sperm into the water simultaneously, creating underwater snowstorms of reproductive cells that turn the sea milky white. This mass spawning event synchronizes reproduction across entire reef systems, increasing the chances that eggs will encounter sperm from different colonies. The timing is so precise that scientists can predict spawning events to within a few days, and divers travel from around the world to witness the phenomenon. The released gametes rise to the surface, where fertilization occurs, and the resulting larvae drift on currents before settling on suitable substrate to begin new colonies. This strategy of overwhelming the water with reproductive cells helps ensure that at least some survive the gauntlet of predators waiting to feast on the bonanza. Coral spawning is one of the ocean's great synchronized events, a reminder of the complex biological clocks that govern life beneath the waves. Some corals form symbiotic relationships with algae that provide them energy. Most reef-building corals depend on tiny algae called zooxanthellae that live within their tissues in one of nature's most intimate partnerships. These single-celled algae photosynthesize like plants, converting sunlight into sugars that they share with their coral hosts. In return, the coral provides the algae with shelter, protection, and access to the nutrients they need to photosynthesize. This symbiosis is so efficient that it allows corals to thrive in tropical waters that are otherwise too nutrient-poor to support much life. The brilliant colors of many corals come from their zooxanthellae, and the health of the partnership is visible in the vibrancy of the reef. When corals become stressed by high temperatures or pollution, they expel their zooxanthellae in a process called bleaching, turning white and often dying if the stress persists. The symbiosis between corals and their algae is a marvel of evolutionary cooperation, but it is also vulnerable to the rapid environmental changes occurring in our warming ocean. Coral skeletons record historical climate data like tree rings. Just as trees lay down annual rings that record the conditions of each growing season, corals deposit layers of calcium carbonate that capture the chemistry of the seawater around them. By drilling cores from massive coral colonies and analyzing the chemical composition of each layer, scientists can reconstruct ocean temperatures, salinity, and even the intensity of past hurricanes. Some coral records extend back thousands of years, filling gaps in our knowledge of climate before human records began. The ratio of certain isotopes of oxygen in coral skeletons reflects the temperature of the water when the layer was deposited, while other elements record patterns of rainfall and runoff from land. These coral archives have revealed important information about past El Niño events, volcanic eruptions, and long-term climate trends. Corals are not just living organisms but unwitting historians, recording the ocean's story in their very skeletons. As we lose coral reefs to bleaching and other stresses, we also lose these precious records of our planet's past. Some marine algae can grow over 1 meter per day. Giant kelp is one of the fastest growing organisms on Earth, capable of adding over 0.5 meter to its length every single day under ideal conditions. These remarkable seaweeds can reach heights of over 40 meters, forming towering underwater forests that rival the grandeur of any woodland on land. The secret to their rapid growth lies in their ability to absorb nutrients directly from the water through their entire surface, and their adaptation to the cool, nutrient-rich currents of temperate coastlines. Kelp does not have roots like land plants, but uses a structure called a holdfast to grip the rocky seafloor, while its fronds float upward, buoyed by gas-filled bladders. This rapid growth means that kelp forests can recover quickly from disturbance, regrowing entire ecosystems within just a few years. However, the speed of their growth also makes them sensitive to changes in water temperature, nutrients, and the grazing pressure of sea urchins. Giant kelp forests are among the most dynamic and productive ecosystems on our planet, constantly growing, dying, and regenerating in response to the rhythms of the sea. Kelp forests provide habitat for thousands of species. Beneath the swaying canopy of a kelp forest, an entire world of marine life finds shelter, food, and breeding grounds. The towering fronds create vertical habitat, with different species occupying zones from the holdfasts on the seafloor to the floating canopy at the surface. Fish dart among the fronds, using the kelp as cover from predators and as a hunting ground for smaller prey. Invertebrates cling to every surface, filtering the water and grazing on the kelp itself. Sea otters wrap themselves in kelp fronds while they sleep, anchoring themselves against the current. The forest floor is home to lobsters, crabs, and sea stars, while the upper reaches attract seabirds diving for fish. Kelp forests also support commercial fisheries, providing habitat for species that humans depend upon for food and livelihoods. The productivity of kelp forests rivals that of tropical rainforests, making them essential components of coastal ecosystems around the world. These underwater forests are gardens of life, nurtured by cold currents and shaped by the ceaseless motion of the sea. Seagrass meadows are among the most carbon-rich ecosystems on the planet. Swaying gently in the shallows of coastal waters around the world, seagrass meadows are deceptively simple in appearance but remarkably important to the global carbon cycle. These underwater grasslands can sequester carbon at rates up to 35 times faster than tropical rainforests, locking organic matter away in their sediments for centuries or even millennia. The roots and rhizomes of seagrasses stabilize sediments and trap particles, creating layers of carbon-rich soil that accumulate over time. Seagrass meadows also provide critical habitat for juvenile fish, sea turtles, dugongs, and countless invertebrates, serving as nurseries that support fisheries far beyond their boundaries. The meadows filter water, absorb nutrients, and produce oxygen, improving water quality in coastal zones. Despite their importance, seagrass meadows are declining worldwide, threatened by coastal development, pollution, and climate change. Protecting and restoring seagrass meadows is increasingly recognized as a powerful tool for combating climate change while supporting marine biodiversity. These modest plants are quiet heroes of the ocean, providing services that benefit both marine life and humanity. Mangrove forests protect coastlines and are crucial carbon sinks. Along tropical and subtropical coastlines, mangrove forests stand as living barriers between land and sea, their tangled roots absorbing the energy of waves and storms. These salt-tolerant trees and shrubs thrive in the harsh intertidal zone, where they are flooded twice daily and exposed to intense heat and salinity. The complex root systems of mangroves trap sediments and organic matter, building land and protecting shorelines from erosion. The forests also serve as nurseries for fish, crabs, and shrimp, supporting commercial fisheries that provide livelihoods for coastal communities. Mangroves store carbon at rates comparable to tropical forests, locking organic matter in their waterlogged soils, where it can remain for thousands of years. The dense vegetation provides habitat for birds, reptiles, and mammals, creating biodiversity hotspots at the interface of land and sea. Despite their importance, mangroves are being destroyed at alarming rates, cleared for aquaculture, agriculture, and coastal development. The loss of mangroves leaves coastlines vulnerable to storms and removes vital carbon sinks that help regulate our climate. Mangroves can filter salt out of seawater to survive. Living in seawater would be fatal for most plants, but mangroves have evolved remarkable adaptations that allow them to thrive where fresh water meets salt. Some mangrove species exclude salt at their roots, preventing up to 90% of the salt from entering their tissues. Others allow salt to enter but concentrate it in older leaves that they eventually shed, disposing of the accumulated minerals. Still others excrete salt through special glands in their leaves, where it crystallizes and is washed away by rain or wind. These strategies require significant energy, which is why mangroves grow more slowly in areas of high salinity and faster where fresh water dilutes the sea. The ability to manage salt allows mangroves to colonize habitats where other plants cannot survive, giving them exclusive access to coastal real estate rich in nutrients and sunlight. This salt tolerance has made mangroves essential components of tropical coastlines, providing habitat and protection in environments too challenging for ordinary vegetation. Some marine plants can survive in extreme salinity conditions. The ocean harbors plants and algae adapted to salinity conditions that would kill terrestrial vegetation, from the nearly fresh waters of estuaries to the hypersaline pools of evaporating lagoons. Some seaweeds thrive in tide pools where evaporation concentrates salt to levels far exceeding open ocean water, while others tolerate the dilute waters where rivers meet the sea. Halophytes, or salt-loving plants, have evolved mechanisms to cope with excess salt, including specialized cells that sequester minerals, glands that excrete salt, and adaptations that allow them to balance water uptake in challenging conditions. These adaptations have allowed marine plants to colonize every coastal niche, from frozen polar shores to sun-baked tropical flats. The ability to survive extreme salinity also makes some marine plants valuable for agriculture in saline soils and for treating wastewater. Understanding how marine plants manage salt stress is providing insights that may help us develop crops that can tolerate the increasing salinity of agricultural lands. The ocean's plants are masters of adaptation, thriving in conditions that would overwhelm most life on land. The ocean produces over half of the world's oxygen. Every second breath you take contains oxygen produced by organisms drifting in the ocean, invisible to the naked eye but essential to life on Earth. Phytoplankton, microscopic algae and cyanobacteria floating in the sunlit surface waters, photosynthesize like land plants, but do so on an immense scale. These tiny organisms collectively produce between 50 and 80% of the oxygen in our atmosphere, far exceeding the output of all terrestrial forests combined. The oxygen they release dissolves into the water and eventually escapes into the atmosphere, where it mixes with the air we breathe. Phytoplankton have been producing oxygen for over 3 billion years, transforming Earth's atmosphere from one hostile to most life into the oxygen-rich environment we depend upon today. Their productivity depends on sunlight, nutrients, and stable ocean conditions, making them sensitive to changes in climate and circulation. The ocean is not just a place where life exists, but the planet's greatest oxygen factory, powered by organisms too small to see, but too important to ignore. Phytoplankton blooms are visible from space. When conditions are right, phytoplankton populations can explode in growth, creating blooms so vast that they paint entire regions of the ocean bright green or turquoise. These blooms can cover thousands of square kilometers and are easily visible in satellite images, where they stand out against the deep blue of the surrounding sea. The blooms occur when nutrients are abundant, sunlight is strong, and water temperatures are favorable, often following the seasonal upwelling of nutrient-rich deep water. Some blooms produce toxins that can harm fish, shellfish, and marine mammals, creating dead zones that devastate local ecosystems. Others are harmless and even beneficial, forming the base of productive food chains that support fisheries and wildlife. The colors of the blooms reveal the types of phytoplankton present, with greens indicating chlorophyll-rich algae and milky turquoise suggesting coccolithophores with chalky shells. Phytoplankton blooms are among the most dramatic and dynamic biological events on our planet, visible from the heavens and essential to life in the seas below. The ocean's plankton population is highly sensitive to temperature changes. Plankton are cold-blooded organisms whose metabolism, reproduction, and survival are intimately linked to the temperature of the water around them. Even small changes in ocean temperature can shift the timing of plankton blooms, alter the composition of plankton communities, and disrupt the food webs that depend upon them. Warming waters have already caused plankton populations to shift toward the poles, changing the productivity of fisheries and the feeding grounds of marine mammals and seabirds. Some plankton species thrive in warmer conditions while others decline, altering the balance of the microscopic world in ways that cascade through entire ecosystems. The sensitivity of plankton to temperature makes them valuable indicators of climate change, with long-term monitoring programs tracking shifts that reveal the ocean's response to warming. scientists worry that continued temperature increases could fundamentally alter plankton communities, with consequences for oxygen production, carbon cycling, and the species that depend on plankton for food. The ocean's invisible drifters are sentinels of change, responding to warming in ways that affect all life on Earth. The ocean's microscopic viruses are the most abundant biological entities on Earth. In every liter of seawater float billions of viruses, invisible particles of genetic material that infect bacteria, algae, and other microorganisms. Marine viruses are the most numerous biological entities on our planet, outnumbering all other life forms by orders of magnitude. If you lined up all the viruses in the ocean end to end, they would stretch beyond the nearest galaxy. These viruses play crucial roles in marine ecosystems, killing bacteria and releasing nutrients that fuel plankton growth. They also influence the evolution of their hosts, driving genetic change through horizontal gene transfer and selecting for resistant strains. Marine viruses affect the global carbon cycle by killing phytoplankton and releasing carbon that would otherwise be locked away in living cells. The study of marine viruses is still in its infancy, with most species unknown and their ecological roles only dimly understood. The ocean's viral soup is a hidden world of incredible diversity and importance, influencing life on Earth in ways we are only beginning to appreciate. The surface microlayer hosts a unique community of specialized microorganisms. At the very interface between ocean and atmosphere lies a layer of water thinner than a human hair, yet this microlayer is home to a distinct community of life found nowhere else. The surface microlayer accumulates organic compounds, lipids, and proteins that drift upward from below or fall from the atmosphere, creating a rich broth that supports specialized bacteria, viruses, and microalgae. This thin skin of the ocean influences the exchange of gases between sea and sky, affecting how carbon dioxide, oxygen, and other gases move between the two realms. The organisms living in the microlayer must cope with intense ultraviolet radiation, fluctuating temperatures, and the physical stresses of waves and wind. Some microbes in this layer produce pigments that protect them from the sun, while others have adapted to thrive on the unique chemistry of their environment. The surface microlayer is a frontier between worlds, a place where the ocean meets the sky, and specialized life forms have carved out a niche in the thinnest of habitats. Marine snow is a constant shower of organic material from surface to deep. Throughout the ocean, a gentle rain of particles drifts downward from the sunlit surface toward the dark abyss below. This marine snow consists of dead plankton, fecal pellets, discarded mucus structures, and fragments of larger organisms, all clumped together into delicate flakes that sink slowly through the water column. The journey from surface to seafloor can take weeks or months, depending on the size and density of the particles and the depth of the ocean. As marine snow falls, it is consumed and reprocessed by organisms at every level, with each bite releasing nutrients and carbon into the water. The particles that reach the seafloor provide food for the deep-sea communities that have no access to sunlight or surface productivity. Marine snow also carries carbon from the atmosphere into the deep ocean, where it can remain locked away for centuries. This biological pump is one of the ocean's most important mechanisms for regulating atmospheric carbon dioxide and supporting life in the perpetual darkness of the deep. Some deep-sea creatures can generate their own light. In the eternal darkness of the deep ocean, where no ray of sunlight has ever penetrated, light is a currency that creatures create for themselves. Bioluminescence, the ability to produce light through chemical reactions, is one of the most common adaptations in the deep sea, found in everything from bacteria to fish to giant squid. Some creatures use their light to attract prey, dangling glowing lures in the darkness like anglerfish with their luminous appendages. Others flash to startle predators or produce clouds of glowing particles to confuse attackers. The light comes in many colors, from the blue-green most common in the deep, to the rare red of dragonfish that can see their own light while remaining invisible to others. Some deep-sea organisms can control their light with remarkable precision, turning it on and off, changing its color, or directing it through lenses and reflectors in their bodies. Bioluminescence transforms the dark ocean into a world of living lanterns, each light a signal in the silent blackness of the deep. The mesopelagic zone is known as the twilight zone due to low light. Between the sunlit surface waters and the complete darkness of the abyss lies a realm of perpetual twilight, where enough light filters down to see but not enough to support photosynthesis. The mesopelagic zone, extending from about 200 to 1,000 meters deep, is home to one of the largest migrations on Earth. Each night, countless fish, squid and crustaceans rise from the twilight zone to feed in the richer surface waters, then descend at dawn to hide in the darkness below. This daily vertical migration moves more biomass than any other animal movement on the planet, transporting nutrients and carbon between the surface and the deep. The creatures of the twilight zone have evolved enormous eyes to capture the faint light, along with bioluminescent organs for communication and camouflage. The zone is largely unexplored, despite its importance to global fisheries and carbon cycling. The twilight zone is a hidden world of motion and mystery, suspended between the light above and the darkness below. Some deep-sea fish have transparent heads to help them see prey above. One of the strangest adaptations in the deep sea belongs to the barreleye fish, whose head is completely transparent, filled with a clear, fluid-filled dome. This see-through skull allows the fish to rotate its tubular eyes upward, peering through its own head to spot the silhouettes of prey swimming above. The barreleye lives in the twilight zone, where faint light from above can reveal the shadows of potential meals. Its eyes are extremely sensitive, capable of detecting the slightest movement against the dim glow filtering down from the surface. The transparent head also protects the fish's eyes from the stinging cells of siphonophores, jellyfish-like creatures whose tentacles the barreleye often steals food from. This bizarre adaptation demonstrates how evolution finds creative solutions to the challenges of life in the deep. The barreleye is a reminder that the ocean holds creatures so strange that they seem to belong to science fiction rather than our own planet. Bioluminescent algae cause the phenomenon called sea sparkle. On warm summer nights in certain coastal waters, waves and wakes can light up with an ethereal blue glow, as if the sea itself were filled with stars. This magical phenomenon, known as sea sparkle or milky seas, is caused by dinoflagellates, single-celled algae that emit light when disturbed by movement. Each tiny organism produces only a faint flash, but when millions are present, the combined effect transforms the water into a glowing blue wonderland. The light is thought to startle predators or attract larger animals that might eat the grazers, threatening the dinoflagellates. Beaches around the world occasionally light up with bioluminescent waves, drawing visitors who wade into the glowing surf and watch their footprints blaze with blue fire. The phenomenon is unpredictable, depending on the concentration of organisms and the right conditions of temperature and nutrients. Sea sparkle is one of the ocean's most magical sights, a reminder that the boundary between science and wonder is often thinner than we imagine. Many marine organisms use bioluminescence to communicate in the dark. In the lightless depths where vision is useless without self-generated illumination, bioluminescence serves as a language of light. Fish, squid, and crustaceans flash patterns of light to attract mates, with each species having its own signature sequence that prevents confusion between similar-looking animals. Some creatures produce sustained glows that advertise their presence, while others create complex displays that pulse and change in ways that carry specific meanings. Deep-sea squid can alter the color, intensity, and pattern of their bioluminescent organs, creating displays as nuanced as any spoken language. The communication happens in 3 dimensions, with animals signaling across distances that would be impossible to bridge with sound or chemistry in the vast ocean. Scientists studying bioluminescent communication have discovered a hidden world of conversation in the deep, where every flash carries meaning and the darkness is alive with silent messages. The deep sea is not a quiet, empty void, but a crowded social world where light speaks louder than words. The blue whale is larger than any dinosaur that ever lived. Gliding through the ocean with a grace that belies its immense size, the blue whale is the largest animal ever to exist on our planet. At lengths exceeding 30 meters and weights approaching 200 tons, blue whales dwarf even the mightiest dinosaurs that ever walked the earth. Their hearts are the size of small cars, pumping blood through bodies longer than 3 school buses parked end to end. A blue whale's tongue alone weighs as much as an elephant, and a human could crawl through its major blood vessels. Despite their enormity, blue whales feed on some of the smallest creatures in the ocean, consuming up to 4 tons of tiny krill each day during feeding season. They were hunted to near extinction in the 20th century, but populations are slowly recovering under international protection. The existence of such giants in our modern ocean is a reminder of the wonders that still swim beneath the waves. The whale shark is the largest fish on Earth and a gentle filter feeder. The whale shark holds the title of the largest fish in the sea, reaching lengths of up to 12 meters and occasionally exceeding 14 meters in exceptional cases. Despite their intimidating size and shark heritage, whale sharks are gentle giants that feed on the smallest organisms in the ocean. They cruise through tropical waters with their massive mouths agape, filtering plankton, fish eggs, and small fish from the water. Their distinctive spotted pattern is unique to each individual, like a fingerprint, allowing researchers to identify and track whale sharks across the globe. These magnificent fish migrate thousands of kilometers following plankton blooms and spawning events, gathering in predictable locations that have become destinations for divers hoping to swim alongside them. Whale sharks grow slowly, mature late, and produce few offspring, making them vulnerable to overfishing and accidental capture. The whale shark is a living reminder that the largest creatures on Earth can also be among the most gentle. The sperm whale has the largest brain of any animal. Deep beneath the surface, sperm whales navigate the ocean with brains that weigh up to 8 kilograms, the largest of any animal that has ever lived. These remarkable organs are 5 times heavier than human brains and feature complex folds and structures that scientists are still working to understand. Sperm whales use their massive brains to coordinate hunts for giant squid in the pitch-black depths, communicate across vast distances with clicks and coders, and maintain social bonds in family groups that can last a lifetime. The forehead of a sperm whale contains an organ called the spermaceti, filled with oil that was once highly prized by whalers, and may help the whale focus and project its powerful sonar clicks. Sperm whales can dive to depths exceeding 2,000 meters, holding their breath for over an hour while hunting in conditions that would crush and suffocate other mammals. Their intelligence, social complexity, and remarkable adaptations make sperm whales among the most fascinating creatures in the ocean. Giant barrel sponges can live for thousands of years. On Caribbean reefs and in other tropical waters, giant barrel sponges grow slowly over centuries, some reaching ages that rival the oldest trees on land. These filter-feeding animals can measure more than 2 meters across and pump thousands of liters of water through their bodies each day, extracting bacteria and organic particles for food. Unlike corals, which can bleach and die quickly under stress, barrel sponges are remarkably resilient, recovering from damage and persisting through environmental changes that devastate their neighbors. The oldest barrel sponges may have been filtering the Caribbean waters since before Columbus first crossed the Atlantic, silent witnesses to centuries of change in the ocean around them. Sponges are among the oldest animal groups on Earth, with a fossil record stretching back over 600 million years. Despite their simplicity, lacking nervous systems, muscles, and organs, sponges have thrived for eons and continue to play important roles in reef ecosystems. Giant barrel sponges are living monuments to the power of patience and persistence in the natural world. The Greenland shark can live for more than 200 years. In the frigid waters of the North Atlantic and Arctic Ocean, the Greenland shark moves with glacial slowness through a life measured in centuries. Recent research using radiocarbon dating of islands proteins has revealed that Greenland sharks can live for at least 400 years, making them the longest-lived vertebrates known to science. Some individuals alive today may have been born during the reign of James I, swimming the same waters before the Mayflower ever set sail. These sharks grow at a rate of about 1 centimeter per year and may not reach sexual maturity until they are well over a century old. Their slow metabolism, adapted to the near-freezing waters they inhabit, may be the key to their extraordinary longevity. Greenland sharks are rarely seen, spending most of their time in the deep, dark waters of the Arctic and only occasionally venturing into shallower depths. These ancient mariners remind us that time moves differently in the cold darkness of the northern seas. Whale songs can travel thousands of kilometers underwater. In the vast expanses of the ocean, sound travels faster and farther than it does in air, and whales have evolved to exploit this property with songs that can cross entire ocean basins. Humpback whales produce complex sequences of moans, cries, and howls that can last for hours and carry through the water for distances exceeding 3,000 kilometers. Blue whales produce low-frequency calls so deep that humans cannot hear them, yet these rumbles can travel across entire oceans, allowing whales to communicate across distances that would take weeks to swim. The songs change over time, with populations gradually adopting new phrases and patterns that spread from whale to whale across the seas. Male humpbacks sing most intensely during breeding season, but the precise function of their songs remains a mystery that scientists are still working to unravel. The ocean is filled with whale song, a chorus that has been playing for millions of years and continues today despite the noise of ships and sonar. Whale songs are the longest, loudest, and perhaps most mysterious conversations on Earth. Many marine mammals use complex vocalizations for communication. The ocean resonates with the voices of dolphins, whales, seals, and sea lions, each species communicating in its own dialect of clicks, whistles, barks, and groans. Dolphins produce signature whistles that function like names, allowing individuals to call to each other across the water. Orcapods develop distinct vocal dialects that are passed down through generations, marking family groups as clearly as human accents mark regional origins. Harp seals gather in the thousands on ice floes, where the air vibrates with calls that help mothers and pups find each other in the chaos. Bearded seals produce haunting warbling songs that travel through the Arctic waters, advertising their presence to potential mates. These vocalizations are not simple reflexes but learned behaviors that require practice and refinement, suggesting a capacity for vocal learning that is rare in the animal kingdom. The complexity of marine mammal communication hints at rich social lives and cognitive abilities that we are only beginning to appreciate. Beneath the waves, a world of conversation unfolds in frequencies both higher and lower than human ears can detect. Sea otters use rocks as tools to open shellfish. Floating on their backs in the kelp forests of the Pacific coast, sea otters demonstrate tool use that rivals the capabilities of primates on land. They select flat rocks from the seafloor, place them on their chests, and hammer shellfish against the anvil with remarkable precision. Each otter has its preferred rock, often tucked into a fold of loose skin under the armpit when not in use, and some individuals will use the same tool for years. Otters can crack open sea urchins, clams, mussels, and abalone, accessing the nutritious meat inside shells that would otherwise be impenetrable. This behavior appears to be learned from mothers, who demonstrate the technique to their pups over months of careful tutoring. Tool use is rare among marine mammals, making sea otters exceptional in their ingenuity and adaptability. The image of an otter floating on its back, pounding shellfish with a chosen rock, is one of the most endearing examples of animal intelligence in the natural world. Dolphins can recognize themselves in mirrors. When scientists place mirrors near dolphin tanks, something remarkable happens. The dolphins investigate their reflections with behaviors that suggest they understand they are looking at themselves. They turn, twist, and examine parts of their bodies that would otherwise be invisible, like humans checking themselves in a bathroom mirror. Dolphins marked with temporary paint spots spend more time in front of mirrors, apparently inspecting the marks on their own bodies. This capacity for self-recognition was once thought to be unique to humans and great apes, but dolphins have joined a small club of animals that pass the mirror test. Self-recognition suggests a level of self-awareness and cognitive sophistication that sets dolphins apart from most other animals. Dolphins also demonstrate other signs of intelligence, including problem-solving, cooperation, and the ability to understand symbolic language in experimental settings. The mirror test is just one piece of evidence that dolphins possess minds far more complex than their simple smiles suggest. Some sharks can detect electrical fields produced by other animals. Every living creature generates faint electrical fields through muscle contractions, nerve impulses, and the beating of its heart. Sharks possess an extraordinary sensory system that allows them to detect these fields, using specialized organs called ampullae of Lorenzini, clustered around their snouts. These jelly-filled pores are so sensitive that sharks can detect electrical fields as weak as a billionth of a volt per centimeter, equivalent to sensing a battery from thousands of kilometers away. This sixth sense allows sharks to locate prey hidden beneath sand, navigate using Earth's magnetic field, and detect the faintest signs of life in murky water. The ampullae are particularly useful for hunting in conditions where vision and smell are compromised, giving sharks an edge in the perpetual darkness of the deep or the clouded waters near river mouths. This electroreception has evolved independently in several shark species and is among the most sensitive detection systems in the animal kingdom. Sharks truly sense the world in ways that humans can barely imagine. The great white shark has a slow reproduction rate, making it vulnerable. Despite their fearsome reputation, great white sharks are surprisingly vulnerable to population decline because of their slow and cautious approach to reproduction. Female great whites do not reach sexual maturity until they are around 15 years old, and they give birth to only a handful of pups every 2 to 3 years. This means that each individual shark represents a significant investment of time and energy, and the loss of a single adult has a disproportionate impact on the population. Great whites are also slow-growing and long-lived, taking decades to reach full size and potentially living for over 70 years. Their low reproductive rate means that populations cannot recover quickly from overfishing, accidental bycatch, or deliberate culling. Conservation efforts for great whites require long-term commitment and patience, as any recovery will take generations. The apex predator of the ocean is paradoxically fragile, its power masking a vulnerability that threatens its future. Oceanic whitetip sharks are among the most bold species around humans. Once considered the most abundant large predator on Earth, the oceanic whitetip shark has a reputation for boldness that sets it apart from most other sharks. Unlike the cautious approach of many shark species, oceanic whitetips will investigate unfamiliar objects and potential prey with a persistence that can seem aggressive. They are open ocean sharks, rarely approaching coasts but often appearing around shipwrecks and drifting boats, leading to a dark history of interactions with humans in the aftermath of maritime disasters. Oceanic whitetips were responsible for many of the attacks on survivors of ships sunk during the Second World War, earning them a fearsome reputation among sailors. Their boldness is an adaptation to the open ocean, where food is scarce and any potential meal must be investigated thoroughly. Unfortunately, this same boldness has made them vulnerable to fishing pressure, and their populations have declined by over 90% in recent decades. The oceanic whitetip's fearless nature is both its defining characteristic and the trait that has brought it to the brink of endangered status. Sharks play vital roles in maintaining healthy ocean food chains. As apex predators, sharks occupy the top of marine food webs and exert a powerful influence on the structure and health of ocean ecosystems. By preying on the sick, weak and slow, sharks help maintain the fitness of prey populations and prevent any single species from dominating. Their presence forces prey to change their behavior, moving away from areas where sharks hunt and allowing overgrazed habitats to recover. When shark populations decline, the effects cascade through the food web, often with unexpected consequences. In some areas, the loss of sharks has led to explosions of ray populations that devastated shellfish beds, collapsing fisheries that had sustained communities for generations. Healthy shark populations are associated with healthy reefs, productive fisheries, and balanced ecosystems, while their absence signals trouble. Sharks are not mindless killers, but essential architects of ocean health. Their presence, a sign that the ecosystem is functioning as it should. Protecting sharks is not just about saving one species, but about preserving the intricate balance of life in the sea. Some jellyfish can live forever through biological immortality. In the warm waters of the Mediterranean and beyond, swims a creature that has seemingly conquered death itself. Torotopsis dohrnii, the immortal jellyfish, possesses the remarkable ability to revert to its juvenile polyp stage when stressed, injured, or simply old. Through a process called transdifferentiation, its adult cells can transform into completely different cell types, essentially allowing the jellyfish to begin its life cycle anew. This biological reset can theoretically be repeated indefinitely, making the immortal jellyfish potentially the only truly immortal animal on Earth. The jellyfish is tiny, measuring only a few millimeters across, and is easily overlooked in the vastness of the ocean. Scientists are studying its cellular regeneration mechanisms in hopes of understanding aging and developing medical applications for humans. Of course, the immortal jellyfish is not truly immune to death, as it can still be eaten by predators or killed by disease. But its ability to turn back its biological clock makes it one of the most extraordinary creatures in the ocean. Some fish can change their gender as they mature. On coral reefs around the world, fish routinely accomplish something that would be impossible for most animals, changing from one sex to another as they grow and age. This sequential hermaphroditism is common among reef fish, with some species starting life as females and becoming males later, while others do the reverse. Clownfish live in hierarchical groups where the largest individual is always female. If she dies, the dominant male transforms into a female to take her place. Wrasses and parrotfish often start as drab females before transforming into brilliantly colored males that dominate territories and mate with multiple partners. The change involves not just reproductive organs but also behavior, coloration and body size, a complete transformation triggered by social cues. This flexibility allows fish to maximize their reproductive success across different life stages and social situations. The phenomenon challenges our assumptions about the fixity of sex and reveals the remarkable plasticity of life in the sea. Some sea stars can regenerate entire bodies from a single arm. If a sea star loses an arm to a predator or accident, it can regrow the missing limb over time. But some species take this regenerative power to an extreme, able to regrow an entire new body from just a single severed arm. As long as a portion of the central disc remains attached to the arm, the fragment can slowly develop into a complete, functioning sea star. This remarkable ability has made sea stars famously difficult to eliminate. Fishermen who once tried to kill sea stars by chopping them up only succeeded in multiplying their numbers. The regeneration process is slow, taking months or even years to complete, but the result is a fully formed individual genetically identical to the original. Scientists are studying sea star regeneration to understand how such complex tissues and organs can regrow, with potential applications for human medicine. Sea stars remind us that the rules of healing and growth we take for granted do not apply to all life on Earth. Some fish can change color rapidly for camouflage or communication. Among the most visually stunning adaptations in the ocean is the ability of certain fish, squid and octopuses to change color in the blink of an eye. Cuttlefish can shift through a rainbow of hues and patterns in milliseconds, using specialized cells called chromatophores that expand and contract to reveal different pigments. This ability serves multiple purposes: camouflage against the sea floor, warning signals to predators, and elaborate displays during courtship. Some species can even display different patterns on different sides of their bodies, courting a female on one side while warning off a rival on the other. The neural control of these color changes is extraordinarily sophisticated, involving rapid processing of visual information and coordinated control of millions of individual chromatophores. Octopuses can match not only the color, but also the texture of their surroundings, raising bumps and ridges on their skin to blend seamlessly with coral or rock. These masters of disguise transform themselves moment by moment, living canvases painted by the demands of survival and reproduction. Certain fish can survive in both saltwater and freshwater. Most fish are adapted to live in either freshwater or saltwater, but not both, as the challenge of regulating internal salt levels in different environments requires specialized physiology. However, some species, known as euryhaline fish, can tolerate dramatic changes in salinity and thrive in habitats ranging from the open ocean to inland rivers. Salmon are perhaps the most famous examples, hatching in freshwater streams, migrating to the sea to grow and mature, then returning to freshwater to spawn. Their bodies undergo remarkable physiological changes during each transition, adjusting kidney function, gill cells, and drinking behavior to maintain the proper balance of salt and water. Bull sharks are another exceptional species, able to swim from the ocean into freshwater rivers, sometimes traveling hundreds of kilometers inland. This adaptability opens ecological opportunities closed to most fish, allowing euryhaline species to exploit resources and habitats in multiple environments. The ability to move between salt and fresh water is a testament to the remarkable flexibility of life in the ocean. Some squid can use jet propulsion to escape predators at high speeds. Squid are among the fastest swimmers in the ocean, capable of explosive bursts of speed that leave predators grasping at empty water. They achieve this velocity through jet propulsion, drawing water into their mantle cavity and then expelling it forcefully through a narrow siphon. The direction of the siphon can be adjusted to steer, allowing squid to dart backward, forward, or sideways with remarkable agility. Some species can reach speeds exceeding 40 kilometers per hour, and certain flying squid can even launch themselves out of the water and glide through the air for distances of up to 50 meters. This ability to escape through flight gives them an advantage over aquatic predators that cannot follow them into the air. The jet propulsion system is an ancient adaptation, evolved long before fish developed the fins and tails we associate with fast swimming. Squid are living rockets, their streamlined bodies and powerful jets making them some of the most effective escape artists in the sea. Many marine animals use Earth's magnetic field for navigation. Across the vast and apparently featureless ocean, countless creatures navigate with precision, using an invisible map written in the planet's magnetic field. Sea turtles, salmon, sharks, and even some whales possess the ability to detect the strength and orientation of Earth's magnetic field, using this information to find their way across thousands of kilometers. The mechanism behind this magnetic sense is still being studied, with theories ranging from magnetic crystals in the brain to chemical reactions in the eye that are influenced by magnetic fields. Marine animals use magnetic navigation to return to the beaches where they hatched, to find feeding grounds across ocean basins, and to migrate along routes that have been followed for millions of years. The magnetic field provides both a map and a compass, allowing animals to determine their position and their heading relative to their destination. Human technology has only recently developed the ability to detect magnetic fields with the precision that these animals achieve naturally. The ocean is crisscrossed with invisible highways that only those with the right senses can perceive. Sea turtles can travel thousands of miles using magnetic navigation. Female sea turtles return to the exact beach where they hatch to lay their own eggs, even after spending decades wandering the open ocean. This remarkable feat of navigation relies on the turtle's ability to detect subtle variations in Earth's magnetic field, essentially imprinting on the magnetic signature of their birth beach. As they travel, turtles read the magnetic map of the ocean, following gradients and contours that guide them across thousands of kilometers of open water. Experiments have shown that turtles exposed to magnetic fields mimicking distant locations will swim in the direction that would take them home from those locations. The precision of this navigation is extraordinary, with turtles arriving at beaches only a few hundred meters wide after journeys spanning entire ocean basins. Sea turtles have been following these magnetic routes for over 100 million years, navigating by the same planetary field that has guided countless generations of their ancestors. Their journeys are testaments to the power of evolution to develop senses far beyond human experience. Some fish can see ultraviolet light invisible to humans. While humans perceive a narrow band of the electromagnetic spectrum, many fish see a world painted in colors we cannot imagine. Certain species possess photoreceptors sensitive to ultraviolet light, allowing them to detect patterns on other fish that are invisible to the human eye. Some fish display ultraviolet markings that are used for species recognition, mate selection, or signaling dominance. Cleaner fish and their clients may use ultraviolet signals to coordinate their interactions, with colors that remain hidden from predators that cannot see beyond the visible spectrum. The shallow waters of coral reefs are bathed in ultraviolet light, making this extended vision particularly useful in these brightly lit environments. Even some deep-sea fish have retained ultraviolet sensitivity, though the function in the dark depths is still being studied. The ocean is full of visual conversations happening in wavelengths that human eyes cannot detect, a secret language of light hidden in plain sight. Certain fish use electric fields to hunt or communicate. In murky rivers and dark ocean depths, some fish have evolved the ability to generate and detect electric fields, creating a sense as alien to humans as echolocation is to bats. Electric fish produce weak electrical discharges that create a field around their bodies, and they sense disturbances in this field caused by nearby objects or other organisms. This active electrosense allows them to navigate in complete darkness, detect hidden prey, and communicate with other electric fish through variations in their discharge patterns. Electric eels take this adaptation to an extreme, generating powerful shocks capable of stunning prey and deterring predators. The electric organs are modified muscles that have evolved the ability to discharge simultaneously, producing voltages that can exceed 600 volts. Electric fish demonstrate that senses we take for granted are not the only ways to perceive the world. The ocean and rivers are alive with electrical conversations and sensory landscapes that humans can only detect with sophisticated technology. Some fish use sonic blasts to communicate or deter predators. The underwater world is far from silent, and some fish have evolved to make themselves heard with sounds that can startle, attract, or warn. Snapping shrimp produce one of the loudest sounds in the ocean by rapidly closing their claws, creating a cavitation bubble that collapses with a crack louder than a gunshot. Pistol shrimp use similar mechanisms to stun or kill prey, with sonic blasts that reach temperatures comparable to the surface of the sun for a fraction of a second. Many fish produce sounds by vibrating their swim bladders, grinding their teeth, or rubbing body parts together, creating a symphony of clicks, grunts, and growls. Toadfish produce foghorn-like calls that can be heard from shore, while chorus frogs deafen the water with their collective singing during breeding season. Sound travels faster and farther in water than in air, making acoustic communication particularly effective in the ocean. The sea is a noisy place, filled with the sounds of creatures communicating in ways that humans have only recently begun to record and understand. Some crabs use sea anemones as protective weapons on their claws. Among the most unusual partnerships in the ocean is the relationship between boxer crabs and sea anemones. These small crabs grasp a sea anemone in each claw, wielding them like tiny pom-poms or boxing gloves to ward off predators. The anemone's stinging tentacles provide protection for the crab, while the anemone benefits from access to scraps of food that fall from the crab's meals. If a boxer crab loses one of its anemones, it may tear the remaining one in half, and both pieces will regenerate into complete anemones. Some boxer crabs have been observed stealing anemones from other crabs, engaging in miniature battles over these living weapons. The relationship is so important to the crabs that they will rarely put their anemones down, even when eating or molting. This partnership demonstrates the creative solutions evolution can produce when two species find mutual benefit in cooperation. Boxer crabs and their anemones are a perfect example of how the ocean's creatures have evolved to help each other survive. Some sea slugs can incorporate chloroplasts from algae into their own cells. One of the most remarkable examples of biological theft occurs in certain sea slugs that steal the photosynthetic machinery from the algae they eat. These sacoglossan slugs puncture algal cells with specialized feeding structures and extract the chloroplasts, the organelles responsible for photosynthesis. The chloroplasts are then incorporated into the slug's own cells, where they continue to function, producing sugars from sunlight that nourish the slug. Some species can survive for months on photosynthesis alone, essentially becoming part animal, part plant hybrids. The slugs often display bright green coloration due to the chloroplasts visible through their translucent bodies. This kleptoplasty, as the phenomenon is called, blurs the boundaries between plant and animal in ways that challenge our assumptions about biology. The sea slugs are living examples of how life can borrow, steal, and repurpose the adaptations of other organisms to gain new capabilities. Marine worms build complex tube structures that support coral reefs. Throughout the ocean, marine worms construct elaborate tubes and burrows that contribute to the structure and stability of seafloor ecosystems. Tube worms cement particles of sand, shell, and organic matter into protective cases that can persist long after the worms themselves have died. The accumulated tubes of generations of worms contribute to the complex three-dimensional structure of reefs and other hard-bottom habitats. In some areas, tube worms are the primary reef builders, creating structures that provide habitat for fish, invertebrates, and algae. The burrows of other worms mix and aerate sediments, processing organic matter and recycling nutrients that support the broader ecosystem. Some tube worms form symbiotic relationships with bacteria that harvest energy from chemicals in the water, building massive colonies around hydrothermal vents. Worms are among the unsung engineers of the ocean, constructing infrastructure that supports countless other species. Some crustaceans practice complex mating rituals and parental care. Beneath the waves, crustaceans engage in behaviors as elaborate and tender as any displayed by birds or mammals on land. Male fiddler crabs wave their oversized claws in complex patterns to attract females, each species with its own signature display. Mantis shrimp form monogamous pairs that share burrows and cooperate in raising their young over periods of months. Female lobsters perform elaborate courtship dances and may remain with a male for days, protected in his den while she molts and mates. Many crustacean mothers carry their eggs attached to their bodies for weeks or months, constantly aerating and cleaning them to ensure their survival. Some species of shrimp tend their young after hatching, providing protection and food in ways that resemble the parental care of more familiar animals. These behaviors reveal rich social lives hidden beneath shells and carapaces, challenging the assumption that invertebrates are simple automatons. The ocean's crustaceans have evolved complex family lives that are only now being fully appreciated by scientists. Some marine birds rely on ocean currents to travel vast distances. The albatross is the master of effortless travel, using the wind and waves of the Southern Ocean to circle the globe without ever needing to flap its wings. These magnificent birds have the largest wingspan of any living bird, reaching up to 3.5 meters, and they use this span to soar on the air currents that flow above the ocean surface. By exploiting the difference in wind speed between the surface and higher altitudes, albatrosses can travel thousands of kilometers while expending almost no energy. Some individuals have been tracked circumnavigating the entire southern hemisphere in just a few weeks, following prevailing winds and currents that carry them around the world. The relationship between ocean and atmosphere creates the conditions that allow these epic journeys, with currents driving winds that the birds have learned to read and ride. Albatrosses can live for over 60 years, spending almost their entire lives at sea and touching down on land only to breed. These birds are living embodiments of the connection between sky and sea, their survival dependent on patterns of wind and water that span the planet. The ocean's tides affect some animal reproductive cycles. The rhythmic rise and fall of the tides has shaped the biology of countless marine species, synchronizing reproduction with the cycles of the moon. Gronion, small silvery fish of the California coast, ride high tides onto sandy beaches to spawn, timing their arrival to coincide with the highest tides of each lunar cycle. The eggs are buried in the sand, developing in the moist environment until the next high tide washes the hatching larvae back into the sea. Horseshoe crabs gather in the thousands on Atlantic beaches during spring tides to mate and lay eggs, following a rhythm set by lunar cycles that has remained unchanged for hundreds of millions of years. Corals time their mass spawning events to particular phases of the moon, releasing eggs and sperm in synchronized bursts that maximize the chances of fertilization. The tides provide a reliable clock that organisms can use to coordinate behaviors essential for survival and reproduction. The gravitational pull of the moon, transmitted through the ocean, organizes life in ways both subtle and profound. Sea cucumbers play a vital role in recycling nutrients on the ocean floor. Creeping slowly across the sea floor, sea cucumbers are the vacuum cleaners of the ocean, ingesting sediment and extracting organic matter that has drifted down from the waters above. These soft-bodied relatives of sea stars and urchins process enormous quantities of sediment, breaking down detritus and releasing nutrients that would otherwise be locked away. Their feeding activity mixes and aerates the sediment, improving conditions for other organisms living on and within the seafloor. In some habitats, sea cucumbers are responsible for processing nearly all of the organic matter that reaches the bottom, making them essential components of the deep-sea ecosystem. Despite their unglamorous appearance and lifestyle, sea cucumbers support the health of the ocean floor in ways that are only now being fully understood. Some species are harvested for human consumption, leading to overfishing in many regions and disrupting the nutrient cycles they maintain. Sea cucumbers remind us that every creature, no matter how humble, plays a role in the intricate web of ocean life. There are more historical artifacts underwater than on land. For as long as humans have sailed the seas, ships have sunk beneath the waves, taking their cargoes, crews, and stories to the ocean floor. Estimates suggest that millions of shipwrecks lie scattered across the world's oceans, from ancient merchant vessels in the Mediterranean to warships lost in battles across the centuries. Each wreck is a time capsule, preserving artifacts in conditions that would cause them to decay on land within years. The cool, oxygen-poor waters of the deep ocean can preserve wood, metal, and organic materials for centuries, offering archaeologists windows into the past that are unavailable on the surface. Beyond ships, entire cities have been claimed by the sea as coastlines shifted, earthquakes struck, and sea levels rose. The ocean floor is an underwater museum of human history, holding treasures and tragedies that are only beginning to be catalogued. Every dive to a wreck is a journey back in time, to moments frozen by the sea. Sunken cities lie preserved beneath the waves. Throughout history, earthquakes, volcanic eruptions, and rising sea levels have sent entire cities sliding beneath the waves, where they remain preserved in the underwater darkness. The ancient Egyptian city of Heraklion, once a thriving port at the mouth of the Nile, lay hidden beneath the Mediterranean for over 1,000 years before its rediscovery by divers in the early 2000s. Its temples, statues, and harbor infrastructure remain remarkably intact, protected by layers of sediment from the forces of decay. In the Mediterranean, dozens of ancient harbors and settlements are now submerged, victims of tectonic activity and changing coastlines. Off the coast of Japan, mysterious underwater structures have sparked debates about their origins, natural or man-made. These sunken cities offer unique opportunities to study the past, with artifacts and architecture preserved in conditions impossible to replicate on land. The ocean has claimed these places as its own, but it has also protected them, holding history in suspended animation for future generations to discover. The ocean floor preserves artifacts in remarkable condition. The conditions at the bottom of the ocean, while hostile to humans, are remarkably gentle on certain materials that would quickly degrade on land. Cold temperatures slow the chemical reactions that cause decay. Low oxygen levels prevent the growth of bacteria and fungi that consume organic matter. Sediments bury and protect objects from mechanical damage. Wood, leather, fabric, and even paper have been recovered from shipwrecks in conditions that astonish archaeologists, their preservation a gift of the deep. The Titanic's debris field contains leather shoes and porcelain plates that look almost new despite over a century on the seafloor. Ancient Greek ships have yielded perfectly preserved cargoes of amphoras, bronze statues, and navigational instruments. The ocean is not a destroyer of history but a guardian, locking away the past in conditions that museums struggle to replicate. As technology improves our ability to explore the deep, we are gaining access to treasures that have waited patiently in the darkness for their stories to be told once more. The ocean's microplastics are widespread and impact marine life at all levels. Plastic debris in the ocean does not simply disappear, but breaks down into ever smaller fragments that persist in the environment for centuries. These microplastics, defined as particles smaller than 5 millimeters, have been found in every part of the ocean, from the surface waters to the deepest trenches. They accumulate in the bodies of organisms at every level of the food chain, from microscopic zooplankton to great whales. Scientists have documented microplastics in the tissues of fish, shellfish, seabirds, and marine mammals, raising concerns about the effects on their health and reproduction. The plastics themselves can carry toxic chemicals that concentrate as they move up the food chain, potentially affecting animals far removed from the original source of pollution. Microplastics have been found in sea salt, drinking water, and the fish on our plates, making this an issue that connects the ocean to human health. The scale of microplastic pollution is staggering, with estimates suggesting that trillions of particles float in the surface waters alone. Plastic pollution can enter the food chain through tiny organisms. The journey of plastic through the marine food web begins with the smallest creatures, the zooplankton and filter feeders that cannot distinguish plastic particles from their natural food. Copepods, krill, and larval fish ingest microplastics, filling their stomachs with indigestible material that can reduce their ability to feed and grow. When these small organisms are eaten by larger predators, the plastics transfer up the food chain, accumulating in tissues and organs. By the time plastics reach top predators like tuna, sharks, and marine mammals, concentrations can be many times higher than in the surrounding water. The chemicals associated with plastics, including additives and pollutants absorbed from seawater, also concentrate through this process of biomagnification. Studies have found plastic in the stomachs of over 90% of seabirds examined, and in virtually all sea turtles tested. Plastic pollution is not merely an aesthetic problem, but a pervasive contamination that threads through the fabric of marine life. Ocean currents can spread pollutants across international boundaries. The same currents that distribute heat and nutrients around the globe also carry pollutants far from their sources, making ocean pollution an inherently global problem. Debris dropped into the sea off the coast of one country can wash up on beaches thousands of kilometers away, carried by currents that pay no attention to political boundaries. The Great Pacific Garbage Patch, a vast accumulation of plastic and debris in the North Pacific, collects waste from countries around the Pacific Rim, concentrated by circulating currents into a region of incredible pollution. Chemical pollutants like mercury and persistent organic compounds also travel through the ocean, accumulating in polar regions and in the bodies of animals far from any industrial source. This transboundary nature of ocean pollution means that no nation can solve the problem alone, requiring international cooperation and coordinated action. The ocean connects all coasts, and pollution in one region inevitably affects ecosystems and communities elsewhere. The currents that have shaped Earth's climate for millions of years now carry the fingerprints of human industry to every corner of the sea. The ocean's dead zones are growing due to pollution and climate change. In coastal waters around the world, areas of extremely low oxygen are expanding, creating dead zones where most marine life cannot survive. These hypoxic regions form when excess nutrients from agricultural runoff and sewage stimulate massive blooms of algae that die, sink, and decompose, consuming oxygen in the process. The result is water too oxygen poor to support fish, crabs, or most other animals, driving mobile species away and killing those that cannot escape. More than 400 dead zones have been identified worldwide, and their combined area has roughly doubled each decade since the 1960s. Climate change is making the problem worse, as warmer waters hold less dissolved oxygen, and stratification reduces mixing that would otherwise replenish oxygen from the surface. Some dead zones appear seasonally and dissipate when conditions change, but others have become permanent features of the ocean. The expansion of dead zones represents one of the most dramatic ways human activities are altering the fundamental chemistry of the ocean. Ocean acidification can affect fish behavior and predator avoidance. Beyond its effects on shell-building organisms, ocean acidification is altering the behavior of fish in ways that could have profound consequences for marine ecosystems. Laboratory experiments have shown that fish raised in acidified water can lose their ability to detect the chemical cues that warn them of nearby predators. Some fish exposed to elevated carbon dioxide levels become bolder and less cautious, venturing into dangerous areas they would normally avoid. Others lose their sense of smell or become confused about which direction to swim, reducing their ability to find food and mates. These behavioral changes occur because carbon dioxide affects the chemistry of the brain and nervous system, interfering with the neurotransmitters that control behavior. The implications are concerning, as fish that cannot detect or avoid predators are more likely to be eaten, with cascading effects through the food web. Ocean acidification is not just a chemical problem but a neurological one, altering the minds and behaviors of the ocean's inhabitants in ways we are only beginning to understand. Certain marine bacteria can break down plastic, offering hope for cleanup. Amid the growing crisis of plastic pollution, scientists have discovered that some marine bacteria have evolved the ability to break down plastics, offering a glimmer of hope for future cleanup efforts. These microorganisms produce enzymes that can cleave the chemical bonds in certain plastics, converting them into simpler compounds that can be further degraded. Researchers have identified bacteria on the surface of floating plastic debris that appear to be actively consuming the material, though the process is slow by human standards. In the laboratory, scientists are working to enhance these enzymes and develop systems for large-scale plastic degradation. Some approaches involve engineering bacteria to produce more efficient enzymes or to survive better in the open ocean. While biological solutions are not a replacement for reducing plastic production and improving waste management, they could become valuable tools in the fight against plastic pollution. The ocean's own microscopic inhabitants may eventually help us clean up the mess we have made. The ocean can generate energy through tidal power and wave energy. The restless motion of the ocean, driven by the gravitational pull of the moon and the energy of the wind, represents a vast and largely untapped source of renewable power. Tidal power stations harness the predictable rise and fall of the tides, channeling water through turbines that generate electricity with remarkable reliability. Unlike solar and wind energy, tidal power is entirely predictable, with the timing and magnitude of tides known centuries in advance. Wave energy devices capture the motion of surface waves, converting their kinetic and potential energy into electricity through a variety of innovative mechanisms. Some systems use floating buoys that bob on the waves, while others employ underwater turbines or oscillating water columns. The energy potential of the ocean is enormous, with estimates suggesting that wave and tidal power could meet a significant fraction of global electricity demand. Developing this potential presents engineering challenges, as the ocean environment is harsh on machinery and maintenance is difficult. But the promise of clean, renewable energy from the sea continues to drive research and development around the world. Some marine algae can produce biofuels offering sustainable energy potential. The tiny algae that float in the ocean's surface waters may hold the key to a more sustainable energy future. Certain species of algae can be grown in controlled conditions to produce oils that can be converted into biodiesel, replacing fossil fuels with a renewable alternative. Algae grow rapidly, doubling their biomass in just hours, and can be cultivated on non-arable land using seawater or wastewater. Unlike crops grown for biofuel on land, algae do not compete with food production for fertile farmland or fresh water. Some species can also produce hydrogen gas directly, offering another pathway to clean energy. The carbon dioxide absorbed by algae during photosynthesis balances the carbon released when the biofuel is burned, making algal biofuels potentially carbon neutral. Commercial-scale production faces challenges, including the cost of cultivation and harvesting, but research continues to improve efficiency. The ocean's microscopic plants, which have been producing energy from sunlight for billions of years, may become valuable allies in our transition away from fossil fuels. More species live in the ocean than on land. The diversity of life in the ocean is staggering, with estimates suggesting that the sea is home to a greater variety of species than all terrestrial habitats combined. Marine environments harbor representatives of nearly every major group of animals, from sponges and jellyfish to fish, mammals and seabirds. The ocean contains entire phyla of animals found nowhere on land, including echinoderms like sea stars and urchins, and cephalopods like octopuses and squid. The three-dimensional nature of the ocean, with habitats ranging from sunlit surface waters to the abyssal depths, creates opportunities for specialization and diversification that are impossible on land. Coral reefs alone support over a quarter of all known marine species, earning them the title of rainforests of the sea. Yet the vast majority of the ocean remains unexplored, and scientists estimate that millions of species await discovery in the depths. The ocean is the greatest reservoir of biodiversity on our planet, a living library of evolutionary experimentation spanning over 3 billion years. The ocean's biodiversity remains largely undiscovered. Despite centuries of exploration and decades of advanced technology, most marine species have never been described by science. Estimates suggest that we have identified only a fraction of the ocean's inhabitants, with millions of species still waiting to be named and studied. Each expedition to the deep sea brings back new creatures, many so strange that they challenge our understanding of what life can be. Entire ecosystems, like hydrothermal vent communities and deep-sea coral gardens, were unknown until recent decades. The microscopic world of the ocean is even less understood, with new species of bacteria, viruses, and protists being discovered constantly. This vast unknown represents both a scientific frontier and a conservation challenge, as we cannot protect species we do not know exist. The ocean is the last great wilderness on Earth, and its hidden diversity is a treasure that we are only beginning to explore. Every new discovery reminds us how much remains to be learned about the world beneath the waves. The ocean continues its ancient rhythms, unchanged since before life began. Long before the first living cell emerged from the primordial soup, the ocean was already in motion, driven by forces that continue unchanged to this day. Tides rose and fell in response to the moon's gravity, currents circulated heat around the globe, and waves broke upon ancient shores. The chemistry of seawater was already being shaped by volcanic eruptions, mineral dissolution, and the cycling of gases between sea and sky. When life finally appeared, it adapted to these rhythms, synchronizing reproduction with the tides, migration with the currents, and feeding with the cycles of day and night. The ocean's rhythms have remained stable through ice ages and warm periods, through mass extinctions and the emergence of new species. Today, the same forces that shaped the primordial ocean continue their work, indifferent to the brief flicker of human civilization. The ocean is ancient beyond comprehension, patient beyond measure, and more enduring than any creature that has ever lived within its waters. And in its depths, the rhythms continue, as they have for 4 billion years, and will for billions more. And now the quiet wonders of the ocean begin to gently fade into the stillness of the night. You have drifted through over 100 peaceful truths about Earth's largest habitat. From the deepest trenches where no sunlight has ever reached to the shimmering surface where plankton dance with the sun. From ancient creatures that have outlived the dinosaurs to the delicate chemistry that connects every drop of seawater to the atmosphere above. You have explored underwater mountains taller than any on land. You have met creatures that glow in the eternal darkness and learned how the ocean breathes, moves and shapes the very climate of our world. You are connected to this story. The water in your body has cycled through the ocean countless times across millions of years. The salt in your blood reflects the chemistry of the ancient seas where life first stirred. Every breath you take carries oxygen released by tiny marine organisms, drifting far across the globe. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady. Like the gentle pulse of waves lapping on a distant shore. Like the slow current that moves through the deepest parts of the sea, patient and eternal. Tonight, as you rest, the ocean continues its quiet work. Currents are flowing. Creatures are glowing in the darkness. Somewhere in the deep, hydrothermal vents are releasing warmth into the cold abyss, and life is thriving in places where no light has ever touched. You are a small, warm presence within this vast blue world, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that the ocean has been here since before life began, and will continue its ancient dance long after the last wave of the day has faded into peaceful stillness. Thank you for joining me on this journey through the world's oceans. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of our remarkable planet. There are more wonders waiting. More secrets hidden in the depths and the currents. More gentle truths to drift through on quiet evenings. Rest well, and may the ocean's timeless rhythm keep you company through the night. This has been Drowsy Discovery. Good night.